So let's talk about the stresses and the strains. And to draw the analogy, who works with metals? All of you work with metals? Metals? No? What type of materials? Okay. Who else with metals? There? No? Here? Okay. If you take a piece of, we take a piece of aluminum. Okay? Let's take a piece of aluminum. And then we're going to polish the aluminum very nicely. Okay? We're going to take sandpaper, and we're going to polish it really nice, very flat. Okay? And then we're going to start with very coarse sandpaper, and then finer sandpaper, and then we're going to do like a submicron sandpaper. So we're going to make this almost like a mirror. Okay? And then we're going to apply a little bit of acid. And what's going to happen is that when you do that, and that's called etching, you're going to see these are called grains. Okay? If you do this for a metal, you're going to see this. This is called the microstructure of the material, microstructure. And you're going to see that these are what we call the grain boundaries. Okay? These are the grain boundaries. These are the grain boundaries. Okay? And it's going to look beautiful. I mean, if you do, this is called metallography. If you do a nice job, I mean, these microstructures are incredible. In fact, there is a very nice exhibit of pictures outside, and I'm sure there are some micrographs, so you can probably see some of these things. So these are grains. So if you take a single grain, what you're going to find in a single grain is that the atoms are going to be aligned in a very regular array. Okay? This is what we call a crystal. So each grain is a single crystal. Okay? And inside the crystal, all the atoms happen to be aligned in a very periodic, very well organized way. Okay? In the case of aluminum, if we have aluminum crystallizes in the cubic system. Okay? Something called face center cubic, FCC, which means that if you magnify this, what you're going to find is that all the atoms are arranged in this face center cubic. And this is why the grains are so well organized. So this grain is aligned this way, okay? And then this grain is going to be organized this way, and then this grain probably be organized this way. And the reason why we have grain boundaries is because the organization of the grains is going to be different at the grain boundaries. If you could remove a single grain, this will be a single grain. This will be a perfect crystal. All the atoms are going to be perfectly aligned, okay? And you're going to see this in ceramics, in metals, okay? Any material that crystallizes in an organized way is going to have this type of a structure. Now let's assume that I take a single crystal. I'm going to take a single crystal from this plate, and I'm going to pull it in this direction. And then the question I have for you is, if I plot the stress versus the strain, and just to make it simple, I'm going to cut it to make a perfect rectangular piece. So I'm going to cut it. Okay, I'm going to cut it. And then I'm going to pull it in this direction, and I'm going to plot the stress-strain curve. I'm going to get something like this. Okay? And then I'm going to cut it again, or I'm going to take a new crystal, but I'm going to pull it now in this direction. Am I going to get the same response or a different response? Different response, okay? And that's what we call anisotropy. Anisotropy means that the properties depend on orientation, okay? And this is very clear for crystals. And this is the response of how atoms are arranged. If you pull them in this direction, you're going to get one response. If you pull them in this direction, you're going to get a different response, okay? And that is exactly what happens with composites. The response of composites is going to depend whether you are pulling along the direction where the fibers are oriented or in a perpendicular direction. So if you're an engineer for Boeing, and going back to your question, if you're an engineer for Boeing and you want to know how the fibers should be placed, you have to know what type of stresses the fuselage is going to expect. So that's where finite element analysis comes into the picture. You have somebody with a workstation, and they say, OK, we have the fuselage. It has 30 feet in diameter. It's going to have internal pressurization. We're going to see some torsion if there is a storm, and there are stresses when the plane is going through a storm. We're going to have some bending. It can be combined bending torsion. There's going to be some vibration. You put that into the workstation, and then you calculate the type of stresses. And based on the type of stresses that you get, you say, OK, we got to put 2 millimeters in thickness of the material here. We got to put 1.5 millimeters. We can save some weight because the stresses are not so high. That's where it comes into the picture. The question is, how do you calculate those stresses based on the material? So what we're going to see here for the next few minutes is an overview of how do we calculate stresses and strains in systems that are anisotropic. It's not different from the crystal. Okay? In the composite, the same thing happens. So let's assume that we have a plate where the fibers are aligned in this direction. Okay? So this is your prepreg. In your prepreg, all the fibers are aligned in the same direction. And we're going to do an experiment. We're going to go to the instrument machine, and we're going to take a little coupon, and we're going to pull it in tension in this direction. Okay? And we're going to apply some strain gauges to measure a strain, and we're going to measure the strain in this direction, and then the strain in this direction. So this is a plot of a stress in X. We're going to call this the X direction. That's the direction of the fibers. And then Y is going to be the direction normal to the fibers. So if we pull it in tension, we're going to have, before yield, a linear region. EX is going to be the Young's modulus in this direction, okay? And then if you measure the strain in the transverse direction, in the Y, you're going to get this response. Now, if you're an engineer working for Boeing, you are not going to use this type of data. You're only going to design up to the elastic limit, okay? Now, the material may take stresses beyond yield, and that's good. But when you design these things, you don't want them to deform permanently. So all the analysis that you do is going to be based on an elastic analysis. And this is why we only pay attention to the linear portion of the stress-strain curve where the material behaves in an elastic way, okay? And the reason why we don't do that is that doing plastic analysis is very complex. And once you have plasticity, you have damage, and that damage can accumulate. So you are never going to design an airplane where you're going to have damage accumulation in each cycle, because the life is going to depend on the history. So all the design for this structure is going to be based on elastic limits. Now, we can calculate the strain in the X direction using the value of the stress divided by the slope, which is Young's modulus. And that's how we calculate the strain in this direction, in the X direction. And then we can calculate the strain in the transverse direction using the Poisson's ratio, okay? And in this case, we define the Poisson's ratio X as the ratio of the transverse strain Y divided by the longitudinal strain X, okay? That's how we define the Poisson's ratio. So if we start with a material that has a square cross-section, once we pull it, it's going to elongate in this direction, okay? And this is going to contract in the transverse direction. So that's the Poisson's effect in these materials. Now we're going to take the same material, but we're going to cut the coupon in a perpendicular direction. So now all the fibers are going in this direction, and we are going to pull it in this direction, okay? So now we're going to plot sigma y. Y is going to be the direction perpendicular to the fibers. We're going to have here epsilon y, which is the strain in this direction, then epsilon x, which is going to be the transverse direction. So in this analysis, x corresponds to the direction of the fibers, y to the normal, to the transverse direction. And then in this experiment, the strain in the y direction is going to be the ratio of the stress in the y direction divided by Young's modulus in the y direction. Now, if you pay attention here, the modulus EY is going to be different from EX, okay? EX is measured in the direction of the fibers. EY is measured perpendicular to the fibers. And then we also have a Poisson's ratio. We're going to call this Poisson's ratio nu y. Okay, it's going to be the ratio of the transverse strain divided by the longitudinal strain. So now we have two different elastic moduli. We have EY in this direction. We have EX in the direction of the fibers. And then we also have two Poisson's ratio. We have this Poisson's ratio Y, and then we have Poisson's ratio X. Okay? And this is the problem when you have anisotropic materials. For an isotropic material, you only have two elastic constants, Young's modulus and Poisson's ratio, or Young's modulus and shear modulus, or bulk modulus and Poisson's ratio. You only need two elastic constants to describe a material that is isotropic. For a material that is anisotropic, then you need more elastic constants because the properties are going to be depending on direction. And in this case, we are talking at least about different elastic moduli in different directions and also different Poisson's ratio in different directions. Okay, are you guys with me? Now, if we have our specimen oriented this way and we apply a shear stress, okay, we're going to have this stress-strain curve where we apply a shear stress and we have a shear strain. And if you remember the definition of shear stress or stress, they actually change the shape of the object, okay? You form an angle. And in this case, we are going to introduce this shear modulus, okay, which is going to be the ratio of the shear stress divided by the shear strain, okay? Now, let's go back to the case of the fuselage. In the case of the fuselage, you're going to have complex states of stress. You're going to have stresses in different directions. You're going to have stresses in different directions. And then you can calculate your stresses using superposition, because everything that we are doing here is a linear analysis, okay? We are not dealing with plasticity. Everything is linear. Everything is elastic. And according to that, we can calculate the strain in the x direction by taking into account the different stresses both in the x direction, which is the direction of the fibers, and the y direction, which is the direction normal to the fibers. Same thing with epsilon y. It's going to depend on the applied stresses and then our shear stress. And in this case, to simplify, we are only working in 2 dimensions. Okay? If we want to have the real analysis, I mean, if you go to Boeing and you want to do the real analysis, these are 3-dimensional analysis. Here, for simplicity, we are looking at the plate type of structures, and everything is in 2 dimensions. But here is the principle of superposition. Your strains are going to be the result of the applied stresses in the different directions. Your strains are the result of the stress applied in the different directions, and you have your shear strain as a result of your shear stress. And as good engineers, we like to do calculations. So this is a very convenient representation to calculate your stresses, your strains as a function of stresses. So you can have a matrix type of arrangement where you have your strains in the x direction, y direction, and your shear stress. Here you have your stresses in the x direction, y direction, and your shear stress. And then the longitudinal strain is going to depend on the longitudinal stress and the transverse stress through these constants. Same thing with this one. And in this system, you can only introduce shear strains by applying shear stresses. Okay? Now, this is not always the case. It just depends on the level of anisotropy. But in this particular case, your shear strains only result from the application of shear stresses. And this is a very convenient way to represent these relationships, because you can program your system using linear algebra, and you can calculate your stress and your strains using matrices and vectors. So one way of doing this is introducing something called the compliance terms. So these compliance terms are defined by these letters S. This actually, I think this comes from the German. Compliance, they say, well, why don't you use C for compliance? So it's been traditional to use S values for compliance. Is that true? I mean, you speak German. How do you say compliance in German? Is the inverse of a stiffness. Okay. So Young's modulus is a measure of a stiffness. So if something is very stiff, it has a very high value of Young's modulus. If something is very compliant, it has low value of, because stiffness, compliance, we use S values. And then for the stiffness, you're going to see that we're going to use C values. And they are actually the opposite in English. But somebody told me that in German, do you know the story about that, Jose Ignacio? No? OK. So this is the so-called compliance matrix. OK? So the compliance constants give you a relationship between a strain and a stress according to this. OK? So you will check today. Tomorrow you will tell us. OK? And this is the definition. So you know that you are talking about compliance because it's going to be the inverse of the stiffness. And the stiffness is connected to Young's modulus. So something that is very stiff, for example, steel is very stiff. Plastics are very compliant. Cement is very stiff. Paper is compliant. OK? So it could be. I think there may be some truth on that. So tomorrow you will tell us. OK? So you can calculate your engineering constants as a function of your compliance constants, and you can do this. Now you can simplify. And you can introduce this M term, which depends on the two Poisson's ratio values. Okay? And you can calculate your stresses as a function of your strains. Okay? So here we have the strains as a function of the stresses. But if you want to calculate your stresses as a function of your strains, then you can use these relationships. Okay? So the point is that once you know your elastic constants, you can go back and forth. Now, in the case of the fuselage, you may want to calculate your strains because you know the pressure inside the fuselage. You pressurize the fuselage. You know the pressure in megapascals. You can calculate the strains. There may be some applications where you are actually applying a strain, and you want to know what the stress is going to be. And these relationships are going to give you values of a stress as a function of a strain. But once you know your elastic constants, you're all set. They will give you one if you know the other. And let me skip here. So if you want to know your values of a stress as a function of a strain, then you have your stiffness matrix. Okay? This is your stiffness matrix, where we're using Q. Sometimes people like to use C. In this case, they use Q. And these Q constants are going to give you the stresses if you know the strains. And this is how we define these Q values. And this is how we calculate the engineering constants as a function of our Q values. And this is very convenient because once you know these values, you can actually read them in a table. You can put them into a matrix, and then you can calculate. Once you know the strains, you can calculate the stresses. If you know the stresses, you can calculate the strains. And this is what design engineers do. I mean, if you have a bridge, and you know the type of loading, you decide what type of material to use. based on the stiffness or compliance and vice versa, okay? It really boils down to knowing the stiffness values of the material that you're using to design your structure. And once you know them, that's it. And remember that we're only using an elastic analysis, okay? We are not using plasticity. We are assuming that all these airplanes are designed just in the linear regime, where everything is reversible. There is no damage accumulation, and that's really the principle for most design concepts. So if you're an engineer working for Boeing, and you want to make a component, let's say the tail of the 780 of the Dreamliner, your design engineer may tell you, gotta make sure that the wings don't deflect more than 0.02%. What type of material should you use? And then you go to your tables, and you say, okay, should I use graphite epoxy, or should I use boron epoxy? And remember that there are many types of fibers. So you have these T3000 fibers. You have these AS fibers. Or why cannot we use Kevlar, or can we use a Scotch ply? And if you see, depending on the material, the values of stiffness are going to be different. This material happens to be very stiff. These are boron fibers in epoxy, okay? If you want to use Kevlar, the stiffness is much lower. So it just depends on what you're trying to build. In an airplane, you don't want the wings to be doing this. The wings have to be very stiff. And this is why we end up using materials like graphite epoxy for those systems. Now compare these two values. So in the direction of the fibers, the modulus is 181 GPa. In the direction perpendicular to the fibers, the modulus is 10.3. That is a lot of anisotropy. These materials are very, very anisotropic, okay? And if you remember the little cartoon that we had, if we have the fibers running in this direction, if you pull here, most of the fibers are going to be carrying the load. So when you look at the modulus of the fibers of this prepreg in the fiber direction, this is why it's so high. But then if you pull in the perpendicular direction, what you are actually testing is the matrix, okay? This is significant anisotropy. You will never find this level of anisotropy in metals. It is very rare to find this level of anisotropy in metals. It's very rare. This is not quite a factor of let me see, this is a factor of 20, less than 20. This is pretty drastic. I mean, in nature, you never find those levels of anisotropy in metals. And this is why when you are applying the prepreg, you gotta be careful that you don't make the fuselage just in the same direction. What will happen if you make your fuselage with just the fibers in this direction? Now, from a pressurization point of view, this is very good because you pressurize, and then this controls your hoop stresses, okay? But why will you not design your fuselage using this? Why? Very good, okay? If you take this in bending, if you pull this and you compress on the bottom, so if you do this, what responds to the load here? Just the matrix. I mean, the material is very compliant. Very good, okay? So you will never do this. So in fact, if you pay attention to the video that we were looking at, the robot was applying fibers this way, but later on, it's going to start doing something like that, and then something like that, and if possible, something like that. So you want to minimize your anisotropy because of that. In one direction, these materials are extremely strong, very stiff. In the opposite direction, they're going to be very weak, okay? Very compliant. So whenever you see a composite structure, you're going to see multi-directional type of materials.
But you have just said now that they want to minimize the anisotropy, or they use smart anisotropy
That's right. That's a good question. You don't want to have it as extreme, but you want to take advantage of that. So in the case of the wings, I mean, you don't want to make everything isotropic because then you don't gain. But when you do your design, you really maximize. If the fuselage is going to be subjected to some state of stress, if bending is really non-existent, then you do everything like that. But because bending is important, then you put fibers in the opposite direction. How much fibers do you put in this direction versus this direction? It just depends on what your calculations show you. It may be that in this case you have 100 fibers and then just 10 fibers or 20 fibers here. So you reduce the anisotropy just to compensate and take into account that you could have other states of stress that may be. But you don't make the material isotropic because then you really don't gain much advantage. So there's still some level of anisotropy, but this is why you design based on the state of stress. So if you know the stress, I just show you the calculations to calculate the strains. If you know your strains, I just show you the calculations to calculate your stresses, okay? And that's what designers do. They sit on a computer, they crank the numbers, and they look into that one.